So good evening, everyone. Welcome to this event. You're watching a small animation about an event called the Cosmic Zoom, which is going to happen on the net, which is continuing to happen on the net. So check out the webpage of ICTS for more details about these events. Now, friends, welcome to this event. Our speaker today is Professor Sreerup Raychaudhuri, who's an elementary particle physicist from TIFR Mumbai. Sreerup's interests are in electroweak interactions, supersymmetry, extra dimension, dark matter, and collider physics. In each of these endeavors, Sreerup is focused on confronting theory with experiment. And I think many of you will understand that these days in physics, in fundamental physics, it's getting harder and harder to have confrontations of this kind. And it's a very worthwhile and valid endeavor. He's very much interested in pedagogy and outreach, and we are fortunate to have him with us today. On the net, you will find other talks by Sreerup, which are very interesting. For example, there's one on the early history of particle physics in India. It contains a lot of material which is not very well known, especially in India. So today he'll be talking to us about the fundamental building blocks of matter. Sreerup, the stage is yours. Please take over.
Thanks a lot, Sam. And thank you for that very warm welcome and introduction. And I'd like to thank ICTS also for allowing me to give this talk and for letting me share the things which I sort of are very close to my heart with this audience. Let me start by sharing the screen before I share other things. So, has it gone full screen?
Yes, yes.
Okay. So my talk today is about the fundamental building blocks of matter. But in particular, I will talk about the standard model and how that has been developed. So that, of course, will tell us about the building blocks of matter. And that's the story which I would like to tell you. And it's an interesting story. It has its ups and downs. And then there are a lot of questions at the end, which I will all come to in due course. So as you know, when you watch a movie, the cast is shown in the beginning. So I will show you the cast. So the cast consists of the fundamental particles. So what are they? So there is one type of particle which are called fermions, which have spin half. And they are divided into one group, which are called the leptons. And there are charged leptons and there are neutrinos, three of them. So the electron, the muon, and the tau are the charged leptons. The electron, neutrino, muon, neutrino, and the tau neutrino, sort of partners of these, are the three neutrinos. Then there are the quarks, which are denoted by U, D, C, S, and TB. We give them fanciful names: up, down, charm, strange, top, and bottom. But they don't mean anything. They just charged. They correspond to certain quantum numbers. Then there is another class of particles which are called gauge bosons, which are Lorentz vectors. Corresponding fields are Lorentz vectors. So there are the photon, which is probably the best known of them, which is the particles of light. There are the three particles which carry the weak interaction, which I will talk about: the W minus, the W plus, and the Z naught. And then there are 8 gluons, which carry the strong interaction, again, which I will talk about. So there is this total of 12. So it's interesting. There are 12 fermions and there are 12 bosons. But there is a 13th particle, and that is called the Higgs boson. That's different from all the others So these all have spin half, the blue ones. These have spin half. These have spin 1, and the Higgs boson has no spin, spin 0. And this is the last part which was discovered. So I will talk about all of these, how they were discovered, what happened, why we think they exist, and so on. So let's begin the story at the beginning, and let me talk about the earliest discoveries. So right, the very first discovery was the electron. It was discovered by Sir J.J. Thomson in 1897. So that's really quite a long time back. And I'm using the convention that this blue color means a negative charge, orange color will mean a positive charge, and a sort of beige color will mean a neutral particle. So here is a picture. In fact, this is a picture I took myself from Cambridge of the actual apparatus which Thomson used in order to detect the electron. This is the famous, if you've read it, the E by M experiment which Thomson did to detect the electron. Then after that came Rutherford, 1911, so some years after this. So he discovered the proton, which is the nucleus of the hydrogen. And he did that by discovering the nucleus itself. And here is a picture, not taken by me, long before my time, of the actual apparatus which he used to detect the nucleus. This is known as the Rutherford's gold foil experiment. And then this thing was completed by the discovery by James Chadwick in 1932 of the neutron. So one negative, one positive, and one neutral particle. This is the apparatus used by Chadwick to detect the neutron. So all of this is well known, it's textbook material, so I'm not going to go into that too much. But because of these, we had the picture of the atom which we now have. So what is that picture? That is the picture that there is a nucleus in the center, vastly exaggerated in size here, just to make it clear. But that consists of protons. These are the orange ones, and the whitish off-white ones are the neutrons. So a combination of them all sitting very closely packed together forms the nucleus. And then there are the electrons which are around it. And these electrons are sort of not indefinite orbits, but in things called orbitals, sort of in fuzzy areas where it's more likely to find them. But they could in principle be anywhere. So there is some motion of the electrons around it. They're sort of buzzing around the nucleus. Let's see, like, flies buzz around some piece of food. So you should think of the electrons like that. And this picture we owe to the following four people. Essentially, we owe it to Niels Bohr, who understood the quantum nature of the atom, to Schrödinger, who gave us the equation to find out these orbitals, to Max Born, who gave us the interpretation of what the probability interpretation, which tells us what these orbitals really mean. And finally, to Dirac, who made things compatible with relativity and explained to us why the electron has a spin. So with these four people, we have this picture of the atom.
Professor Raychaudhuri, there was a question in the chat box asking what is spin.
Yes. So I will come to it. Spin is basically an intrinsic angular momentum which is held by all these particles. So it can come in units of h bar. So it can be half h bar when I say spin half, h bar when it is spin 1, and of course 0 is always 0. Okay, so it's an intrinsic angular momentum, which is it's a purely quantum mechanical property, as you can see from the fact that it's proportional to h bar. When h bar goes to 0, the spin all disappears. Okay, and the understanding of that comes from making the quantum mechanics compatible with relativity, which was done by Dirac in 1928. So let me go ahead, because atomic physics is not really, we are talking about the fundamental building blocks. So let me try to go into the nucleus. Now, this was a question asked by Heisenberg in 1932, as soon as the neutron was discovered, that look, the protons are all positive. You look at that combination I've shown here, this bunch here. So they're all positive, so they repel each other. The neutrons are neutral. They neither attract nor repel. So in that case, with so many things repelling each other, how does the nucleus stay together? Why doesn't it simply fly apart? Why doesn't it explode? So that was a question asked by Heisenberg. And his answer was that then there must be something which is holding them together, some glue, which is keeping them together. So that must be in the form of an attractive force. there must be a force of attraction between the nucleons. That is, between the protons and neutrons, which is different from the electromagnetic interaction. It's not the typical electrostatic repulsion, but it's some new force which is causing the attraction between the protons and neutrons. And it must be afflicting the neutrons also. If the neutrons did not participate in it, then as the nucleus moved around, some of the neutrons would fly off or they would be left back. So the whole thing adheres together coherently, which means all of them must be participating in this force of attraction. So this interaction, which he just called the nuclear interaction, then later it was called the strong nuclear interaction, and nowadays we just call it the strong interaction. So let's try to estimate how strong is this strong interaction. Okay, simple calculation. Let's look at the potential in a hydrogen atom. So you know that this is the difference, the product of the charges of the electron and the proton, and A naught is the Bohr radius, 4 pi epsilon naught is the permittivity of free space, and if you calculate this quantity, it comes to 13.6 electron volts. Everyone knows this. So now, when we go to the atom, then the force between two protons, it will be similar. The charge is still E, but now the distance is roughly of the size of the nuclear radius. Okay, it can't be more than that. So that's the maximum distance you can have, the nuclear radius. So I can rewrite this simply by dividing and multiplying by A naught. So this quantity, of course, is the same as this. So I know what this is. And I know what A naught and the nucleus size are. And what are they? This quantity is 13.6 electron volts. A naught, which is the Bohr radius, is of the size of about half an angstrom, 10 to the minus 10 meters, an angstrom size. And the nucleus size is about a femtometer, 10 to the minus 15 meters. So this quantity is 10 to the 5, 1,100,000. So the potential, and therefore the force between the proton, the two protons inside the nucleus, is 100,000 times more than the force in an atom. Now, how do we try to understand that? Let's look at this picture. So this, of course, is 1.3 MeV, but so imagine that this is a computer mouse, the kind which is probably in your hand at the moment. And what is the weight of it? It's very light, right? It's a small light object. So if this is the weight of this is the force of an atom, then the weight of a big 10-ton truck would be the weight of the strong interaction. So that's how they compare. It's immensely stronger. And now actually it's of mind-boggling strength, because if you think of the interaction between atoms, the forces between atoms, that's also actually much, much more powerful than we can imagine. Let me just bring it to you by showing an example. You know what this is? The Great Pyramid of Egypt. Okay, so this contains 2,300,000 of stones like this. Each stone weighs 2.5 tons. So now you can calculate the weight of it. Now this whole weight is resting on, after all, on one layer of atoms at the bottom. Why aren't they being crushed? They're not being crushed because of the repulsion between the electrons of one atom and the electrons of the other, which are at atomic distances. So that's roughly the atomic force. So that's strong enough to hold up this enormous structure. And not just this structure. If you go from the pyramid, you go to, let us say, the Himalayas. It's enough to hold up Mount Everest. And now the nuclear force we are talking about is 100,000 times stronger, 100,000 times stronger. So there's no question that it's fair to name it the strong interaction. So now I've introduced you to so we have a new interaction, electromagnetic interactions and the strong interaction. And of course, there was always gravity. I will come to these interactions again later. But let's continue with this voyage of discovery. Now, we learned by studying electrodynamics, or the quantum electrodynamics, that the electromagnetic force can be understood as due to the exchange of virtual photons between charged particles, like protons. And these photons are the quanta of the electromagnetic field. And this idea is called quantum electrodynamics. So let me try to explain it by a cartoon. So imagine that there are these two stick figures, are two skaters on an ice skating rink. So there's ice at the bottom and they're wearing skates. So this guy comes up to the other guy and gives him this ball, throws the ball at him. What happens? When he throws the ball at him, this guy recoils back, and this guy also is pushed back by the momentum of this ball. Now, suppose you couldn't see the ball. What would you conclude? You'll conclude these guys came close together and then repelled each other. There's some force of repulsion between them. So instead of these ice skaters, suppose you have two protons, and then the protons exchange a photon. Result is that they are pushed apart. That's simple. It's simple, basic conservation of linear momentum. This photon which came out with the linear momentum pushes this back. This goes into the other one and that gets pushed back. So the protons are being repelled. We shouldn't take this too literally, but this gives us some idea of what this exchange means. Well, if the electromagnetic force is due to such an exchange, then the strong interaction should also be due to exchange of something. And this is what was pointed out in 1935 by Hideki Yukawa, Japanese scientist. He said that the strong interactions must also be due, but not to the exchange of things like photons, but to the exchange of spinless particles with a mass around 200 times the electrons. So he called them mesotrons. Then that was shortened to mesons. Then it turned out that there's more than one kind of mesons. I'll tell you about that in a moment. So these were called pi mesons, and then people are lazy, so we call them pions. So finally, from mesotrons, they have become pions. And then, just as collisions between charged particles, we know that that leads to emission of photons. That's how the light which is coming from your screen, the light which is in your room, all of that comes from collisions between charged particles. So that leads to the emission of photons. And so similarly, if you have collisions between nucleons, it would lead to the emission of pions. Now, where do collisions between charged particles happen? In 1935, the best place to look for them was to look for them in cosmic rays. Cosmic rays, mostly protons from the sun, which come and hit the atmosphere. There are nuclei of oxygen and nitrogen in the atmosphere. So these protons come and hit those nuclei, and therefore from that, you get out showers of pions. So look for pions that's what Yukawa had said. And in fact, the first people who actually tried to do that were an Indian pair. There was D.M. Bose, who was then the director of Bose Institute in Calcutta, and his student Viva Chaudhuri. They were the first people to try it. And they did find a different kind of meson, which had also been discovered. But unfortunately, they couldn't find the pion because their equipment was somewhat primitive. They were, remember, they were in India, which was a colonized country. They didn't have the best equipment, but they were the first to try to look for it. Then I'll tell you a little more about this cosmic rays. So as I said, typically a cosmic ray comes in somewhere from the sun, and there are a few which come from violent events in the universe elsewhere, active galactic nuclei, supernovae, quasars, and so on. So colliding galaxies. So it comes and hits the atmosphere. So then it hits some nucleus, and a shower of particles comes out of the nucleus. Those particles hit other particles and create more particles. So eventually the energy of this original particle gets dissipated into a shower like this. So this is a realistic shower simulation. This was discovered by Victor Hess in 1912, who actually went up in a balloon and actually measured the fact that there's a lot of ionization, a lot of charged particles in the upper atmosphere. So here is a sort of picture of this kind of shower development. But this idea of shower development was not developed by Hess, but it was developed by Homi Bhabha, who, of course, was the founder of TIFR, where I work, also the founder of ICTS, not the founder of ICTS, but ICTS is a part of TIFR. So in some sense, the founder of everything which leads to leading to this talk. But apart from that, this was Bhabha's scientific contribution with Heitler. They developed this theory of these showers. So you understood. So therefore, you go here and you see there are these pi's, pi minus, pi plus, and so on. So lots of pions to look for. Okay, so take your detector, take whatever cloud chamber, photographic plate, whatever you have, and look for the cosmic rays. But when that was actually done, people first found particles of mass around 105 MeV, which is about 210 times the electron mass. But we now call them mu mesons, and again we are lazy, so we call them muons. They were discovered by Anderson and Niedermeyer in 1937. In fact, this is the first muon track which they published. It was seen in a cosmic cloud chamber. But in 1947, exactly 10 years later, the pions were discovered. They were discovered by Powell and Occhialini, and there were two others also with them. And it's basically a team which discovered it. And when you look at these particular tracks published by them in their paper, only this little track, this tiny one, is the pion. This longer one is a muon. So muon, as you see, leaves a long track. These are electrons at the bottom. So this little track at the top here, this tells you of the existence of the pion. And they were able to identify the pion with Yukawa's meson. So now came a question, of course. Yukawa's meson was understood. It's what gives you the strong interaction. Okay, but what is the muon doing? So Isidore Rabi, he was also a Nobel laureate for Rabi oscillations. He asked this question: who ordered that? Where did that come from? We didn't ask for it. Where did it come? And that's a question which, in some sense, we are still asking. But I'll come back to that. Let's go ahead with the story here. There is another question when you have pions, which you need to ask about the proton. Why doesn't the proton decay into pions? Look at this decay chain. A proton with positive charge decays into a positive pion and a negative and a neutral pion. The pions are much lighter than the proton. So why suppose a decay like this happens? The proton decays into pions. Okay, the masses are fine. The proton mass is 938 MeV by c squared. These are only 135 and 140. So if you add them up, it's far less than the proton mass. So no problem. You should in fact have a proton decaying like this. But it doesn't happen. Of course, if it happened, then all the protons in all the nuclei everywhere, including in your body and my body, would be decaying into pions. So there would be only pions around, no nuclei and none of us. So the fact we know that the proton doesn't decay. So if the proton is not decaying, there must be something which prevents it from decaying. So the answer to this was discovered by Stuckelberg in 1939. What he pointed out, the proton, and there's a whole class of particles like protons, which are called baryons, and that includes the neutron. It carries a conserved quantum number, B, equals 1, which is conserved in all the processes. But pions and other mesons like the pion, we'll talk about them, they have B equal to 0. So in this kind of a situation, the initial state, the P, would have B equal to 1. This final state has B equal to 0. So baryon number, this number, which we call baryon number, is not conserved. And therefore, this decay cannot happen. So the proton, which has baryon number 1, can only decay into a final state where there is something which has baryon number 1. However, of all the particles which have baryon number 1, the proton is the lightest. So there is no lighter particle it can decay into, and that's why it doesn't decay. So it's basically, it cannot give up its baryon number to anybody, and therefore it stays stable. So that's the beautiful idea due to Stuckelberg, and this idea has been used again and again, and we will talk about other cases. Okay. Now, I call the 50s, 1950s, as the fabulous 50s, because in the 50s, basically it's this period, not just the 50s and the center, but from this 1947 to about 1965, much of the grounding base of modern particle physics was set. And as you see, almost every year a new particle was discovered. The pions, the kaons, then the delta, the lambda, sigma, antiproton, neutrinos, these are called cascade or Xi particles, rho, omega, and so on, a long list. So during this period, it turned out that it's not just the proton, neutron, and electron, but there's a whole, not just muon and pion, but a whole host of new particles. There are many, many of them. And they all seem to be of the elementary particles of the same type. So today, we classify all these particles in something in a way which is known as the particle zoo. Why zoo? Let's go to an ordinary zoo. So there are the leptons and the hadrons. So in a zoo, typically you have very light objects like birds, which can fly in the air. You also have light objects which are like small animals, like these rabbits you see here. You'll find them in the zoo. Go to a different section and you will find medium-sized animals like deer. And of course, there are the real heavyweights, like the hippos, the elephants, the rhinos, and so on. And of course, you will also find butterflies flitting around. Gives you this nice environment of a zoo. We've all gone there and enjoyed ourselves. Now, the particle zoo is similar. Among the leptons, the really light particles, like birds, are the neutrinos, the 3 neutrinos. The charged leptons are the next level of heaviness, sort of light, still light. Then we have the hadrons, which includes 2 kinds. Essentially, the first kind are the mesons, which are like sort of medium heavy particles. Meso means medium, so the pions, the kaons, and then the rho A1, and so on. And then there are the heavy ones, the baryohadrons. Hadrons means, actually, we actually use the word baryons here. These are all hadrons. So baryons like the proton, neutron, delta, sigma, and so on. So that's the particle zoo. It consists of 4 types of particles: neutrinos, charged leptons, mesons, and baryons. Sorry, I should have written baryons. And of course, there is the photon. There's the light massless guy who is connecting everybody else. So this was the particle zoo which people understood in the mid-50s or early 60s. But by the early 1960s, there seemed to be at least 30 to 35 elementary particles. And today we know more than 300. So that's a very messy situation, isn't it? If you have to remember the names of 300 particles, I mean, that's even more difficult than learning Chinese. So, in fact, there's a famous quote from Enrico Fermi, who told some student, "Young man, if I could remember the names of all these particles, I would have been a botanist." Well, of course, in botany, you have to remember all these long names, Ficus religiosa and Oryza sativa and so on, of so many different kinds of plants. And so this is not something physicists generally like to look for an order and system rather than to have a large amount of data. I mean, they always want to analyze and have systematize the data. So that's basically what is there in it. There is no disrespect from to botanists. Okay, actually this system was found so, okay, not by Fermi, but by 2 other gentlemen, and I'll discuss that in a moment. So it takes a set of particles called the pseudoscalar mesons, which includes the pions and the kaons, the K mesons, the kaons. So there are two quantum numbers which are called isospin and hypercharge. Let's not worry about what the details are. They are quantum numbers which you can find, conserved quantum numbers carried by these. So if you classify them, then you will find that the pions, the positive and negative and neutral pion, come very nicely along this line. The K plus and K minus come on this line, of course, opposite, equal and opposite because they're antiparticles of each other. And there's the K naught and K naught bar, which are neutral, which also come on this side. So you also find another particle called the eta naught, which competes for the central position. I've just displaced them a little so that you can see both. So with this, you can draw this nice hexagon, and this hexagon contains 8 particles. Okay, there are 6 at the ends and 2 in the middle. So this was known, this way of classifying things gives you what is called the Eightfold Wave. Now, why Eightfold Wave? That was the people who discovered this were Murray Gell-Mann and Yuval Ne'eman, and they both came to this conclusion independently. Incidentally, the golden border shows that this person got the Nobel Prize, but not so important, but just a matter of curiosity. But Murray Gell-Mann was a person who was well read in many things outside of physics. And he had read a lot about Buddhism. And if you have read about Buddhism, you know that the Buddha said that there is an eightfold way of virtue which tells you, which gives the salvation. So he gave this fanciful name, Murray Gell-Mann, to this. He called it the Eightfold Way. Of course, it has nothing to do with Buddhism. It's just a fanciful name. And if you want the technical name, it's the octet or 8 representation of SU3. But that's just technical for anybody who wants to know what the technical name is. The funny thing is that not only pseudoscalar mesons, but if you take vector mesons, they also satisfy this. You can put the 3 rows instead of the pions, the excited kaons instead of the, and once again, you get the omega naught instead of the eta, and once again, you can draw the same hexagon and get the same octet. More important, take the baryons. You can get the same thing with the baryons. Put the proton and neutron here, the sigmas here, and the xis or cascade particles here, and the lambda naught comes in the middle. Same story is repeated. Okay. Now, flashback. Let's go back to the periodic table. Remember that the same properties were repeating. That's why you had a periodic table. And Mendeleev, who first wrote it down in 1869, these were the elements which were known in Mendeleev's time. This was actually the periodic table written down by him. And of course, it's not exactly the modern periodic table, but he put elements with similar behavior, one below the other. And actually, he used it. See, there were these empty places. So he used these to predict the properties of the particles in the empty places. We have all read that in chemistry in high school. And sooner or later, people started discovering those. Scandium, then gallium, and then germanium. And that caused people to take this periodic table seriously. And in fact, after that, gradually, a whole bunch of new particles were discovered, of new elements were discovered, and all fit nicely into the periodic table. So what is the lesson we learned from this? Well, Niels Bohr gave us the answer. The properties of the elements show repetition because they have the same outer atomic structure. You all study that, which is known as the Aufbau principle. And let's take an example. Lithium, sodium, and potassium, alkali metals, all have the same behavior. That's because they have the same outer atomic structure. 1 electron in an s orbital outside. So 1 here, 1 here, and 1 here. So this repetition of the substructure, there is a structure inside them, and when the structure gets repeated, you see the same properties. So Gell-Mann concluded that, okay, maybe that's the reason. And therefore, what he did was that he went one step ahead and took particles which are called the heavy baryons and found that you can arrange them not in an octet, but in a decuplet or in a 10 representation of the C3, same quantum numbers, but now they come like this. There are 4 deltas. There are 3 heavy sigmas. There are 2 heavy cascades. There were 9 of them. So he could draw this triangle, but this was not complete. There was an empty space at the bottom. Now, what does this remind you of? Exactly like the periodic table. And so just by looking at these properties and how the properties change, for example, if you look along this line, you see all these particles are negative, the blue ones. So this particle must be negative. If you actually look at the masses of these particles, they grow heavier as they go down. So this particle must be sort of heavier, and the mass changes by roughly the same amount. So you could predict the mass. So he actually predicted this particle of this mass. And lo and behold, in 1964, people discovered a particle which is called the omega minus, which fits in perfectly with this. It has the right charge, it has the right mass, everything fits in perfectly. So just like people took Mendeleev's idea seriously, when Mendeleev predicted new elements and those elements were found, similarly, people took the Gell-Mann's idea of the Eightfold Wave or whatever very seriously when he predicted a particle and it was actually found to have all those properties. Now Gell-Mann went ahead And this is something which he and George Zweig independently came up with. So as with atoms, he says the repetition of these properties are because they are composites. They have smaller particles inside, and when the same structure repeats, you get the same behavior. So Gell-Mann called them quarks, Zweig called them aces. Okay. So anyway, the name quarks has stuck. So he gave names to these quarks. He called them an up quark, the down quark, and the strange quark. I'll talk about strange, why it's strange a little later. It's not really strange why it's called strange, but we'll come to that. So as you've seen, the size of these are roughly the same. The strange quark I made a bit bigger because it's a little heavier. So now, what happens? How do you construct the mesons and the baryons out of these? Okay, the pion, the pi plus, is a combination of U and an anti-D. Remember, each of these will have its antiparticle, the U bar, the D bar, and the S bar. So the U and D bar give you a pion. They are sort of bound together. Similarly, a D and an S bar will give you the kaon. Two U's and a D will give you the proton. Two D's and a U will give you the neutron, and you can construct all of them. In fact, take this baryon octet. So UUD is the proton, UDD is the neutron, and then each of these you can construct. So these are two different wave functions of the same combination. But as you see, the number of S's is increasing. No S's here, one S and two S's here. So you can write down the quark structure of all these baryons. So now basically you have only three particles. However, there's an interesting, okay. So you know when you said that the atoms consist of electrons and protons, fine. We can prove it. Electrons and nuclei, prove it. You can pull the electrons out, get independent electrons, which is what J.J. Thomson did. So the question which would naturally you would ask is, can we pull the quarks out? Is there an experiment? When you, for example, you break up a nucleus, or you break up a proton, you hit a proton and another proton very hard, it breaks up, do the quarks come out? It turns out that this never happens. This never happens because of a phenomenon called quark confinement. Now, what is that? So we'll take the example, for example, of the rho plus, which is a UD bar state. So the point is, we understand now that there is a potential connecting the U and D bar, which is like similar to a simple harmonic potential. It's not a simple harmonic oscillator, but it grows. It's a bound state potential and it grows with distance. As we know with the harmonic oscillator, the further away you go, the stronger the force, which pulls it back. And of course, because of the bound state, this is not at the zero of sense. You're trying to pull them apart. So you've given them some energy to take it above the bottoms and try to pull them apart. But what happens is that when you pull them apart, as you pull them apart, you're going higher in energy. But at some stage, you have put enough energy to the system, because remember, this is relativistic, that you can create a U and a U bar pair out of the vacuum. Remember, this was the original UD bar. Okay, the original UD bar. And when you moved it out, you see a new U bar and a U came out of the vacuum. You've pulled this, put the extra energy you put in, gets converted into matter. Okay, by the famous equal to mc squared equation. And now you have a UU bar and a UD bar, and these themselves will now coalesce. The UU bar will form, and then these are now at the bottom of their potential. Okay, so you have two new particles, and of course that is the pi naught and the pi. So the decay which happens, if you try to pull them apart, the rho plus can decay to a pi plus and a pi naught. But you have one meson going to two other mesons. The quarks never came out. This happens at the quark level, but it doesn't happen. So I've just written down the thing. So that you cannot separate out quarks. This phenomenon is known as the confinement of quarks. Okay. Now remember this cartoon I showed you. So if there is a force, such a strong force between quarks, it must be due to exchange of something. Not pions, because this is at a much smaller level. This is inside pions. But the quarks which are there, quarks and antiquarks, there must be something which carries that interaction. So those particles we will call gluons. Of course, obvious reason, they glue the pion or the baryon or whatever it is together. So they play the same role as the virtual photons, which are holding the, let us say, an electron and proton system together. It turns out that the gluons, because you have an SU3 kind of mathematical structure, there are three kinds of charges. Like the electromagnetic charge, there's only one kind of charge, but there are actually three kinds of charges for the gluons. And these three kinds of charges lead to 8 kinds of gluons. You can put charges as pairs together. Anyway, let's forget that. So if you look inside a proton, for example, or a neutron or any baryon, what you really have, for example, this is, let's say, a proton. So you have 2 U-type quarks, 1 D-type quark, and then you have a bunch of, sort of hazy, fuzzy material, some kind of gunk inside that, which is always changing. There are lots of gluons. There are virtual particle-antiparticle pairs appearing and disappearing out of the vacuum. It's a dynamic system. It's like a bubbling pot. So you can think of let's say, a pot of some mud or some plasticine kind of thing, which is bubbling all the time. And there are 3 balls inside that. So those 3 balls keep going up and down and all around. Bubbles come up, bubbles burst, go back. So that's the kind of dynamic structure inside a proton. It's not a simple static. And of course, if this is the real strong interaction, then what about the force between 2 protons, which we can model with a pion? That we know that it's similar, that in atoms, there is an attraction between the proton and the electron. And then when you bring 2 atoms together, there is a cohesive force, which is known as the van der Waals force. So that cohesive force is a little bit whatever is left over from the atom as a whole is neutral, but when you bring them close together, there's a little bit of leftover interaction. That's called the van der Waals force. So similarly, when you bring protons together or protons and neutrons together, a little bit of the leftover force from the strong interaction, from the gluon interaction, is what gives you the strong interaction, which holds the Heisenberg interaction. Okay. A little bit about strangeness. Remember, I used the word strange. So people discover that there are these strange selection rules which allow some heavy particle decays to happen, but don't allow others to happen. For example, you see this xi naught particle decaying to a lambda naught and a pi naught. But you never see xi naught decaying to a neutron and a pi naught. See, everything is neutral here, so there's no question of charge. Here are the masses. So 1315, this is the mass of this in MeV by c squared, happily goes to 1116 plus 135, no problem with that. But if it can go to something whose mass is 1116 MeV, it can certainly go to something whose mass is 939 MeV. So there's no problem with energy conservation on. So then why is this decay not happening, this neutron? So go back to the idea of Stuckelberg. If some decay should happen but is not happening, that means there must be a conserved quantum number which is preventing this from happening. And indeed, that was the idea. So this was suggested by Gell-Mann, again Gell-Mann and Pais. And they said there's a conserved quantum number carried by the sigma naught and the lambda naught have it, the neutron doesn't have it. So this quantum number, let's call it S for strangeness. So S is 1 for this, S is 1 for this. So S is conserved here. S is 1 here, but S is 0 on this side. The pion doesn't have any of it. So therefore, because S is not conserved, you don't have this thing happen. So because you have strange selection rules, a fanciful name given to this was strangeness. So Nishijima, another Japanese scientist, came up with the same idea independently, same year. Okay. Now, okay. So therefore, this comes from strangeness, and therefore the quark which carries this property is actually the strange quark. Only one of the quarks has this strangeness, The other two don't have it. So any particle which has this quark will have the corresponding strangeness. All right, let me take this thing a little bit ahead. By 1970, people realized, and by people I mean these pair, and I've also followed the convention that I've used color photographs for people who are still with us, black and white photographs for people who are no more. So these three gentlemen are still with us. They are a little older than they look in the picture. Glashow, I think, is 90, and the others are also in their 80s now. But in 1970, they pointed out that there are some phenomena from which we can conclude that the strange quark, just like the up and down, the U and D, are partners of each other. The strange quark was sort of unpartnered, but they said no. This also has a partner, and it also carries a conserved quantum number. And they gave it, again, a fanciful name like strangeness. They called it charm. So there is a new quark, a fourth quark. Now, this was a postulate, okay, that there should be a new quark called the charmed quark, and that will have a quantum number called charm, which is 1 for the quark. So therefore, certain decays will happen and certain decays will not happen. Now, you could have also a bound state of a charmed quark and an anti-charmed quark. So CC bar bound state. So if you look at this animation, you really see the CC bar. It's like positronium, okay, which is electron, and they are going around their mutual center of mass. It looks very random here, but if you look carefully, you will see that both of them are describing elliptic orbits and going around a common center of mass, which is somewhere here. So if it's like positronium and it has charmed quarks, obviously name for it, call it charmonium. And this charmonium was actually discovered. It will look like a meson because it's a bound state of a quark and an anti-quark. And it was actually discovered by Burton Richter and Sam Ting in 1974. The funny thing is that Richter called it the psi and Ting called it the J. And all of Richter's friends kept calling it the psi of psi. And all of Ting's friends kept calling it the J. So what happened eventually, that so many papers were written with J and so many with psi, that it was decided that we just be given a hyphenated name. We call it the J psi. Okay. So this is the only particle which has a double name. It's called the J psi. But the discovery of this now proved that, of course, now there are 4 quarks. Okay. But this is not the end of the story. So remember that you have the neutron, the neutrino, electron, neutrino, and the electron, that forms a pair. The muon, neutrino, and the muon formed a pair. And you can pair this with the U and D and with the CNS. So basically, this forms one generation of fermion. This is called the first generation. This forms something called the second generation. Okay, end of the story. Why should you expect anything more? So this is where these two Japanese gentlemen, Kobayashi and Masukawa, they won the Nobel Prize for this. They showed that there's a somewhat arcane phenomenon called CP violation, which again I will come to the end of it. But to understand CP violation, you do require a third generation. It can't happen if there are only 2 generations. You will require a third generation. So they predicted without any evidence whatsoever that there will be a third generation. Now, when they predicted in 1973, absolutely no one believed it. In fact, the famous Kobayashi-Masukawa paper, for which they eventually won the Nobel Prize, they couldn't publish it anywhere in any refereed journal. So they actually had to publish it in a paper, in an unrefereed journal where you pay money and just it gets published. But fortunately, they did publish it because, of course, they got huge rewards as a result. Now, after that, some years after that, people started discovering the particles of the third generation. First one to be discovered was the partner, the one corresponding to the electron and muon. It was the charged lepton called the tau minus. It was discovered by Martin Pearl in 1975, and he won the Nobel Prize for it. Then came the B quark, which is the partner of the down and the strange quark. It was discovered in 1977. Then as late as 1994. And in fact, older people in this audience will probably remember that discovery, came the discovery of the top quark or the T quark, which is the partner of the B. And the size of this is roughly according, it gives you the order of masses, but it's not to scale, because the top quark is much, much heavier than all the other quarks. And finally, the remaining particle, which is the tau neutrino, was discovered only in 2001. Okay, we got proof that it exists only in 2001. Now, so therefore, you have these three generations. Same question, which Rabi had asked, why? Why don't we have only one generation? Why do we have three generations? This is a question to which we have no answer. I mean, who ordered the muon? Who ordered the second generation? Who ordered the tau? Who ordered the third generation? We just don't know. We just know that there are three generations. We have no clue. So this is one open question in particle physics. Anyone who finds the answer and can prove it is certainly going to get a Nobel Prize. All right. Now, let's look at the masses of these fermions. I have plotted these masses, and as you will see, this is a logarithmic plot, so it's a huge range. And here is the top quark, right, the more heaviest of them. Then there's a cluster of some of the others, and the neutrinos are at the bottom. First generation, second generation, and third generation. So I've just drawn some lines. So there's a variation over 7 orders of magnitude. The top quark has this mass, neutrino has less than this. So that's okay. You can see that on the graph. The masses, you see something interesting. The masses increase from the first to the third generation. You see, there's a general trend. We don't know about these masses, but you see there's a general trend for the masses to be heavier from first to the second generation and second to the third generation. The quarks are also generally heavier than the leptons. So the quarks of this generation are heavier than the leptons. Okay. However, the pattern is a mystery. Let's try to fit. Okay, how do you explain this graph? There is a pattern, okay? There seems to be some pattern. It's not completely random. But of course, there is too much variation in this pattern to be able to understand. So that's another mystery. And once again, anybody who can understand and explain this mystery certainly is going to get a Nobel Prize. So with this, I've not finished my talk. This is only the end of the first part of my talk. So I've explained to you the ingredients which go into the standard model, all the particles which go into it. Now I move on to the next part, which is about how the particles interact with each other. So of course, we know that there are 4 forces. The first one is gravitation. Discovered the laws of falling bodies were discovered by Galileo, the law of gravitation, and the theory of general relativity, which is the relativistic version of these, all discovered by these famous people. We have electromagnetism. Again, the properties of electricity were discovered by Gilbert. The connection between electricity and magnetism was established by Faraday, and the unified theory of electricity and magnetism, which we call electromagnetism, was discovered by Maxwell. We have the strong interactions, which I've been talking about. So the nucleon-nucleon interactions were postulated by Heisenberg. Yukawa gave the meson theory of exchange, and quantum chromodynamics, which is the theory of gluons and quarks, was developed by Murray-Gell-Mann in 1972. Then we have the weak interactions, which came with the discovery of beta decay by Rutherford. Fermi, who gave the theory of weak interactions, and later Schwinger, who gave the theory of W boson exchanges. I will explain more about this in a moment. But let's try to understand the connection between symmetries and interactions. So this is fundamental to the study of these interactions. Now, what you see here, you see a ball, a green ball, and there's a line in the center which shows you the diameter. So I've set this ball rotating. Can you see it rotating? Well, I can't. It's not rotating, but it is rotating. Why don't I see it rotating? Because it's a round ball. Every configuration which it has is the same. I can't see the difference. So that's why even though this is rotating, you can't see that it's rotating. But let me distort the ball a little. Let me pull it out. Now it's clear that it's rotating, isn't it? So imagine it as an elastic ball. I'll go back. Imagine this is an elastic ball which I pulled out and it's rotating. So now it's clear that the ball is rotating. The difference you can see that the symmetry is not there. But what happens if it's elastic? The elasticity pulls the ball back into that round shape. So now you can either talk about this in a physics language. So the rotation is invisible when the rubber ball is symmetric. And you can see that either you say, use a geometric or mathematical language, then the symmetry tends to get restored. Or you use the typical physics language, there's an elastic force which pulls it back. Now there's no difference between the two. The restoration or the requirement of the symmetry and the elastic force are basically the same thing. So this has proved this idea that a symmetry and a force are intimately connected with each other, that every force essentially tries to restore a symmetry, has been a very fruitful way of looking at elementary interactions. So let me move on a little bit. Come back to, of course, almost every bright idea in modern physics begins with Einstein. And we start with general relativity. What did he say? He said there's a symmetry between all frames of reference. That means the laws of physics appear the same in all frames of reference, including those with relative acceleration. And what restores that symmetry? The presence of the gravitational force. The gravitational force is there so that you get the symmetry back. The result is that just like the rubber ball, the space-time behaves like an elastic membrane. Masses tend to deform it and give rise to a gravitational force which tries to make it flat again. That's giving you the symmetry back. So you have this famous analogy that you can think of space-time as a stretched membrane. Of course, this is two-dimensional, but space-time is four-dimensional. And then a heavy object basically deforms it, and then it gives rise to the gravitational force. Okay, let's move on. And of course, you know that when something like a coalescing black holes, of course, Ajit is listening to me, so I shouldn't be talking too much about this. But when there are ripples in this thing, then you would see them as gravitational waves. That's the great discovery of LIGO recently. Okay, let's go to electromagnetism. What happens with electromagnetism? Remember that in quantum mechanics, Max Born told us that the wave function is a complex number, but only the probability density is the physical measurable, and that's proportional to the modulus. So to understand that, let's look at this. Let's imagine that psi is the wave function, and it has a real and imaginary part, and this is psi with a phase which is going linearly with time. So essentially what's happening, the phase is changing, and if you look at any of the real or imaginary part, they are going as sine waves. So it's like e to the ikx. So it's sine kx plus or I omega t. So it's sine omega t plus cos omega t. So that's the real and imaginary part. But the only thing which is measurable is not this angle, but the length of this line, the length of this rotating line. So that is what is physically measurable. That means that all of the physically measurable things should not care what that angle is. So there is a symmetry, just like when you had your rotating ball, when you made rotations in it, it didn't change anything. So it was exactly the same physics. Similarly, when you have this rotating phase, where the phase changes, nothing changes in physics. So that's the symmetry. What is the consequence of that symmetry? Let's put it like this. All the physical configurations should remain symmetric under a change of the phase of the wave function. Okay, that's the angle. So the restoration of this symmetry, okay, if it looks like it's not going to be symmetric, you'll have to put in a force, and that force is the electromagnetic force. That's what restores the symmetry. So the change of phase is also sometimes called a change of gauge. So the gauge symmetry and the electromagnetic force arises from this gauge symmetry of the wave function. And this theory was developed first in a rudimentary form by Hermann Weyl, basically applied it to gravity, but actually by London and Fock in 1929. Now, it is a bit mind-boggling to think that all of electromagnetism should arise from this fact, that we cannot measure the phase of a wave function. That is the reason for us having electromagnetism. So even if you look at something as spectacular as lightning strikes, remember that this is because you can't measure the phase of a wave function. So it's an interesting thought to carry home. All right, we go to weak interactions now. So we go to processes like beta decay, and Schwinger pointed out that again, these processes require exchange of a charge boson. So typically what happens in the beta decay, a neutron decays to a proton and an electron, and of course there's also a neutrino which comes with it. So basically what he thought is the neutron should be actually, the proton becomes a proton and emits a W. So the neutron goes to a proton and then this W, which is the weak boson, and the W decays to electron and a neutrino. So that's the process which happens. I'll repeat it again. The neutron goes to a proton and the W comes out, and then the W decays to an electron and a neutrino. So that's what you see is beta decay. But of course, the W has to be charged, right? This is neutron is neutral, proton is charged. So the W has to have minus charge. And that decays to an electron, which also has a minus charge. So that means there are two. There must be a W plus and a W minus. But now, if you are going to have such exchange boson, there's an exchange force. So there must be an underlying symmetry. And he guessed that it must be a gauge symmetry. And because there are two kinds of W, a plus and a minus, there must be more than one kind of charge. So Schwinger went this far, but the theory was carried on by Glashow, who was Schwinger's student. And he pointed out that the only valid way in which you can write down a gauge interaction which can explain the weak exchange bosons is to combine it with electromagnetic theory and have 4 gauge bosons in a unified electroweak theory, it's called. So you have the W plus and W minus, you have a Z naught, which is a new boson which comes in, and of course you have the photon. So these 3 give you the weak interaction, this gives you the electromagnetic. But they are a unified theory at some energies. But why do these forces become separate? Okay, they become separate. They are separate because these W's and Z's have mass and the photon is massless. Why does that happen? Well, if you go back to a gauge theory, any gauge symmetry, and this was originally discovered by Pauli and later rediscovered by Sieniak, that any gauge symmetry demands that the gauge boson be massless. So if gauge bosons are massless, the force becomes a long-range force, 1 by r, like the Coulomb force. But if they are massive, the force becomes short-range. It becomes like a Yukawa interaction, minus r over lambda, where lambda is proportional to 1 over m. So if m is 0, okay, then this is 1. This quantity is 0, so e to the 0 is 1. So then it's 1 by r. So if m is infinite is 0, then you get a 1 over r. But if as m becomes heavier and heavier, then you have a shorter and shorter range of the interaction. And we know that the weak, so gauge interaction would permit only long range interactions. But we know that the weak interactions are short range interactions. So what's going on? So let's try to understand this. So let's come back to this example of the elastic ball. So suppose you took this elastic ball and it, let's say, it grew a little bit of a pimple on one side. Okay, a little projection. Now, of course, the symmetry is broken. Okay, so if it rotates now, there's no question that it's rotating. You can see that going around. Okay, so a projection breaks the rotation symmetry of the elastic sphere. Similarly, a mass term, a mass of the W or Z would break the gauge symmetry of the universe. Okay, I mean, these particles comprise the universe, so therefore it would break the gauge symmetry. So therefore, what would he say? The gauge symmetry would prevent it from happening, right? It would prevent, just like if you pinch out something from a rubber ball, take a rubber ball, pinch out a section, let it go, the gauge force will draw that back, just like it drew this thing back. It will just draw it back. So similarly, the elastic force will cause this thing to disappear. So similarly, gauge force will cause the mass terms to vanish. You want to allow masses to happen. The perfect analogy. So what's going on? But we do know that weak interactions are short range and the weak gauge bosons must be massive. So how can we have this? So there is something wrong with the theory. Big question mark. And this problem took some years to solve. But the solution when it came was beautiful. And it took us to a different branch, came from a different branch of science, which is condensed matter physics. So imagine you took the same rubber ball and you put it in liquid nitrogen. Okay, liquid nitrogen fumes, and you cooled it. If you cool it, the rubber ball froze. The rubber ball froze and it causes a phase transition. It no longer has the elastic property, it becomes a rigid thing. Okay. So similarly, when the universe cooled, it underwent a phase transition. And now, with this frozen ball, if you pinch out a section, it will remain like that, because the elasticity has been lost in this new phase. So similarly, when the universe cooled after this new phase, the gauge symmetry wasn't there anymore. It was there to begin with, but it went away. So in this new phase, mass terms could arise, and you could have mass for the W and Z. So this theory, of course, the original theory was derived by Landau and Ginzburg in 1937, but in 1960, the fact that weak interactions could be explained by this was derived by Nambu and Jonah-Lasigno. Of course, this is a picture of Nambu when he gave the theory, and this is a picture of Jonah-Lasigno as he is now. So, of course, Nambu was the professor and Jonah-Lasigno was the student. Okay. But you will actually ask this question, that what was it which underwent this phase transition? What is the rubber? What is corresponding to the rubber of the ball? And this is the idea which came up, that there must be a field which does this, there must be a particle which does this. So the first people to propose it were Engler and Brout, then Higgs, and Gralnick, Hagen, and Kibble, all in the same year, within a few months of each other. And what did they say? There must be a spinless field pervading the universe. This underwent the phase transition as the universe cooled, and this field broke the electroweak symmetry and acquired a mass. The temperature at which it acquired it, very different from liquid nitrogen. It is this huge quantity, which is known as the electroweak transition temperature. Okay, so that's a million billion, so a million billion Kelvin. But there is something more which was pointed out by Higgs alone. And what Higgs pointed out is that these particles will also give you a spin zero boson, and you can detect it through the electroweak interactions. So look for it. You'll be able to find it. And this particle, of course, we call this, therefore called the Higgs boson. Okay. And if this happens, then people have started looking for the Higgs boson. So initially, for various theoretical reasons, we knew that the Higgs boson was not lighter than 1 GeV and not heavier than 800 GeV. But 1 to 800 is a huge range to look for, and it took 48 years to keep looking for it. So over the years, this range kept getting narrowing as people did more and more experiments. And eventually it narrowed down, and the boson was finally found in 2012. It has 125 GeV mass. The machine where it was done, the Large Hadron Collider, you see a cutaway view of this. It's a huge machine which is there at Geneva in Switzerland. And there are people from every country, almost every country in the world working on it. More than some 6,000 people needed to run this giant collider, all to find that one tiny particle of mass, 125 GeV. Here is the jubilation you can see. This is when this gentleman here with his hands raised, he's the Director General he was the Director General of CERN at that time, Rolf Feuer. And actually, I remember what he said. He raised his hands and said, "Gentlemen, I think we have it." And if you see, there's one old man sitting here and clapping. That is Peter Higgs. Okay. Now, let's go a little bit ahead with this. So Weinberg and Salam, they also pointed out that it's not just the Higgs, but the fermions also acquire mass through the Higgs boson transition. And the stronger the interaction with the Higgs field, the greater the mass. So, okay, I'll come to this graph. So, if you read the story of Vikram or Vetal, and Vikram carrying the Vetal on his back. So, these fermions essentially carry Higgs bosons in their backs. So, the stronger the interaction, the more the number of Higgs bosons which are sitting on their backs. And the Higgs boson has a mass. So, therefore, the stronger the interaction with the Higgs field, the more the mass. And here's the proof of that. On this side, you're plotting the strength. This is experimentally determined strength of the interaction with the Higgs boson. This is the mass, and you find that it comes on almost a perfect straight line with all these particles, top W, Z, bottom W, and so on. There are some errors, of course, because of the experimental data, but this is a fairly recent graph, and it shows you that this theory, in fact, is indeed correct. So this is now what we call the standard model, but I'll come to that. Okay, then we have just seen that for strong interactions, what is the symmetry? Every quark carries 3 quantum numbers, which we call colors. And so the U quark is actually 3 kinds of, it's like a red, blue, and green U quark, but they are not real colors. Okay, they are quantum numbers. And mixing up of these quantum states doesn't change the physics. So we have symmetry under color transformations. To preserve this symmetry, we require 8-gauge bosons as before, gluons, and this gauge series called quantum chromodynamics. I've already showed you Gell-Mann. And these are Fritsch and Lloyd-Wheeler, who wrote that famous paper in 1972. So when we put all these together, we have the standard model: 6 quarks, 6 leptons, 3 weak bosons, 1 photon, 8 gluons, 1 Higgs boson, and then electroweak gauge interactions, color gauge interactions. There's a Higgs self interaction, which is responsible for the phase transition, Higgs fermion interaction, which give us the mass of the fermions. Possibly, if there's gravitation, which we know there's possibly a graviton. If there are gravitational waves, perhaps there's a graviton. Then there are these 2 other somewhat obscure things called parity violation and CP violation, which I won't discuss, but these are also not demands. These are, so all these ingredients together have to be put together and they form the standard model. Now, they are not related to one another. It's not that, one demands the existence of the other, the phenomena demand it. So it's really a phenomenological model which has been constructed. It's extremely successful. I'll come to that. But this model, if you think of it, it reminds me of this house. I don't know how many of you can recognize this house. It's in Bombay. It's in my city, and it belongs to the richest man in India. And perhaps there is art in it, but to me, it looks like different houses and one have been piled on top of the other without relation to the one below. So the standard model is like that. It's also very successful, like the person who owns this house is a very successful person. But somehow, I personally wouldn't want to build a house like this. So let's come to the success part first. The standard model has been extraordinarily successful in explaining the results of all terrestrial experiments done so now. Here is a picture from experiments, and you can see that the extent to which things which are not standard model are ruled out. So basically tells you that standard model holds up to all these energies. Okay, so there are literally hundreds of tests which it has passed. There is no reason to think that it is not the correct description of fundamental particles and their interactions at energies up to about a TeV, which is, as per TeV means a tera-electron volt, which is a billion electron volts, which is as far as current experiments can go. So do we then have a complete theory of fundamental particles and interactions? Can I stop and finish the talk now? Sadly, answer is no. So a few more minutes. And again, I'll take you through a quick flashback. In the 1894, Robert Millikan, the famous Millikan, said, it seems probable that most of the grand underlying principles have been firmly established. We all know everything. And he further says the further truths of physical science are to be looked for in the 6th place of decimals. So we know everything. And shortly after that came the quantum revolution, came the nuclear physics, came relativity, everything of 20th century physics came after that. In a strange echo, can you recognize this person? This is Stephen Hawking in his youth, before he developed his sickness. In 1993, almost 100 years later, he says, although we have not found the exact form of all the physical laws, we already know enough to determine what happens in all but the most extreme situations. Different language, but roughly the same sentiment. He also added that he gave a 50-50 chance that we will find the exact laws in the next 20 years. So next 20 years took us to 2013. We are almost at 2023. We haven't found the exact laws yet. So why am I saying this? So let me now take you to the other extreme, to the universe at large. The first puzzle is that of dark matter. It seems that every galaxy which you see each these objects are galaxies, and it sort of seems to be immersed in a cloud of dark matter. Okay, you don't really see this dark matter. This is just a simulation. What you actually see is something like this, because the dark matter is dark. But you can see it through other things like the gravitational interactions. So therefore, this dark matter seems to have only gravitational and maybe weak interactions. And there actually seem to be galaxies which are composed only of dark matter. So there's a lot of dark matter in the universe, and the standard model has no particles which can explain dark matter. So big something missing. So people are trying to do experiments to see if every galaxy is immersed in dark matter, the Earth is also immersed in dark matter. So you just make a machine, and if it has weak interactions, you expect the dark matter at some stage, some incoming dark matter particle to come and interact with your detector. Maybe an electron will come out, and then in the detector it will give you a flash. So hopefully, so people have been doing these experiments, but no success so far. We have not seen any particle of dark matter. We know it's there, but we haven't been able to detect it directly. So that's one big question. What is dark matter? What could it be? The second question is about dark energy. So we know, of course, that the universe was created in a big bang. So initially there was a fireball that expanded. And then after some time, when it expanded, it cooled. It formed all these nice filaments. And eventually all these filaments coalesced, and you have the universe which you have today, with galaxies far apart, and each galaxy has stars and other things inside. Now, if you try to do the mathematics of this, then as the universe expanded, there's a radius which expanded. So the radius today is about 46.5 billion light years. But the expansion followed a certain rule, which is called Hubble's law, that the rate of expansion, the rate of change of this radius, is proportional to the radius itself. Okay, so that's really an exponential growth, logarithmic growth. So, and this h is Hubble's constant. The rate of change is proportional to the radius. Now, if that happens, this is that h is known as Hubble's constant. So people try to measure this. But now if you look at this blue line represents Hubble's constant. This is the rate on one side, this is the rate on this side, and this is the distance. And the fact that the actual points are a little bit off this actually shows you that this rate of change is greater than h. So the expansion is not at a uniform rate, but is actually accelerating. And this was discovered by these three gentlemen in 1998. They won the Nobel Prize for it later. And it's known as the accelerating universe. But why would the universe? This would require some matter which actually is pushing the universe apart. And that is some matter with mutual repulsion, which we just call dark energy. We have no clue what it is. And the standard model has no particles which can explain dark energy. So that's the second big question. There is a third question, which is the question of antimatter. So, of course, immediately after the Big Bang, you know that radiation converted to matter. Famous equation. The basic standard model interaction for this conversion largely do not distinguish between particles and antiparticles, which means you should have produced as many antiparticles as particles. But we don't see antiparticles, right? The universe is composed of matter. If you had antiparticles, they would be annihilating. We would be annihilating all the time. So Sakharov, the Russian scientist, pointed out in 1967 that yes, there is a bit of asymmetry between particles and antiparticles, and that happens in weak interactions. It's not there in gravity or in strong or electromagnetic interactions. It's there in weak interactions, and that's known as CP violation. Now, CP violation, of course, can be accommodated. That's where Kobayashi and Maskawa came in, because there are three generations. We know there are three generations today, and in fact, the experiments have shown that there is an asymmetry between particles and asymmetry for weak interactions. This is the famous graph, and only the little bit of error here shows, otherwise that in the theory. So it's predicted to the perfect. So the fact that you have a non-zero value of this triangle proves that there is CP violation. But the size of this triangle also tells you that this is the level of asymmetry between matter and dark matter. But is that what we see? No. We see 100%, we see 100% matter and 0%, almost 0% antimatter. So then this number should have been close to 100%. So you should have had much, much more CP violation in the universe than we are seeing. So what's going on? Again, the standard model doesn't tell us, and we don't. Then there is something called the mass hierarchy problem. That's simple to understand. A free or non-interacting Higgs boson, remember we thought of it as a sort of sticky thing which sticks to fermions, it will also stick to itself. So a free Higgs boson would travel as a classical particle, straight line at constant speed, as given by Newton's first law. But interaction will call it to pull antiparticle, particle, antiparticle pairs out of the vacuum. And those will keep collecting. So as the Higgs goes, it will actually become heavier and heavier. It's like walking through mud. Your shoes become more and more mud, and that mud picks up more and more mud. So basically, your shoes become heavier and heavier as you keep walking. So the Higgs suddenly becomes intolerably heavy. Where will this process stop? It will stop where the Higgs boson has become as heavy as the heaviest particles in the theory. And those we know will happen when the gravitational interactions become as strong as the electromagnetic interactions, that is at the Planck mass. Now that's the value of the Planck mass. And that's the value of the Higgs mass. So why is the Higgs mass only 125 GeV, and why is it not shot up here? Many, many, many orders of magnitude more. We don't understand this. Okay, this should have happened. It's not happening, so there must be something which prevents this from happening. Okay, the fifth and last problem is the issue of vacuum stability. So the potential energy due to the Higgs boson changes shape as the energy increases. That's something which happens in a quantum field theory. So let's suppose this is the energy of the process. And at the kind of energies we have now, okay, this is the shape of the Higgs potential. Okay, so you see that there are minima here. So we are sitting in one of these minima somewhere here. This is where the universe is. But as the energy goes up, you see, this becomes steeper and steeper. And so, but it still goes up, but at some very high, some energy, there is this thing overturns. And this potential goes down to minus infinity. But if there is no minimum potential, particles can also go down to minus infinity. That means they can emit an infinite amount of energy, and the universe would simply burn up in one flash. That's what you call a catastrophe. Now that catastrophe hasn't happened. Moreover, initially, you know that you were after the Big Bang, you were at a very high energy. So if this had been the nature of the vacuum, then you would never have cooled down. So therefore, we know that this is not happening, and therefore something is happening which is keeping the vacuum stable. Again, it's a tantalizing hint, but we don't know. So all of this gives food for thought. There seems to be something. The standard model works very well, but it doesn't answer all these very fundamental questions, especially when we go to the universe at large. It's good for terrestrial experiments up to a certain energy. So, of course, a lot of thought which has gone into it, a lot of theoreticians have ideas. And here is a sort of chart created by somebody, okay, which I have stolen from this blog, but in fact, I did already see forgotten the host. So it has many, many ideas have come. There is supersymmetry. There are extra gem. There are sterile neutrinos, MSSM, right-handed neutrino. There are things which have not been thought of yet, I'm sure. Majorans, axions, lots of theory, none of which has been verified yet. Hopefully it will be. I myself have worked on some of these theories. Okay, one day perhaps we'll know whether they're right or wrong. But all of this, I hope I have been able to convey to you that we do know a little bit about the universe. Still a lot to know. So let me conclude with the famous words of Newton. I do not know how I may seem to the world, but to myself I seem to have been only like a boy playing by the seashore and diverting myself, and now and then finding a smoother pebble or a prettier shell than ordinary, whilst the great ocean of truth lay undiscovered before me. So perhaps some of the younger people who are listening to me will discover some more pebbles, more prettier shells, or perhaps some part of the great ocean itself. So on that note, I'll end this talk. Thank you very much for listening. I've gone way over time, but still, I hope you did enjoy the talk. Thank you.
Thank you for the talk. And there's a large number of questions, and unfortunately, we don't have time to cover all of them. Let me just ask.
So should I look at the chat box or what?
No, I will just take a selection of the questions which are in the chat box. Because
so if you read them out, it will help.
Yeah. I'll read out the questions. One question is from Chandrasekhar. While comparing the strong and the electromagnetic interactions, you use the electromagnetic charge rather than some strong charge. So he would like an explanation of why that was done.
Oh, okay.
Right at the beginning of the talk.
Well, okay, let me explain. So basically, I said that protons repel each other. That's electromagnetic repulsion. But the strong interaction holds them together. So the point is that since the nucleus is stable, protons are not moving with respect to each other, then these two must balance. So if I want to calculate the strength of the strong interaction, which is the attraction, then I can simply calculate the repulsion and say it's equal to that. So that's what I did. I calculated the electromagnetic interaction, which I know, and that gave me the value. But it's just an estimate, of course.
Yeah. The next question is from Anshuman Pandey. Why the neutron does not exist in the free state? The neutron, why is it unstable?
It does. It does, but it's unstable because of the weak interaction. So you see, anything which can decay will decay. You can't stop it from decay. The neutron is a baryon. So if there is a baryon which is lighter than the neutron, it will decay into the baryon. There happens to be a baryon which is lighter than the neutron. That's the proton. So it decays into that. All the baryons you saw in my talk, they are all unstable. They all decay and eventually you get a proton at the end of the thing. The proton can't decay because there's nobody the poor fellow can decay into. That's the reason.
Well, there's a question from Avni Sejwal. Why is gauge symmetry important in the first place? Why shouldn't it break?
What is Higgs symmetry? Symmetry is the gauge symmetry. So gauge symmetry, why is it important? It seems I don't know the answer to that. That seems to be the way nature is. There are gauge symmetries. The gauge symmetries exist. Just like gravitation, the symmetry, the general gauge invariance, general quantity invariance exists. That's the way the world is. So can't tell you more than that.
Well, the next question is about from Alok. He's asking about the G-2 experiment of the muon. He would like you to comment on this. It's going to be discussed by Fermilab tomorrow.
Yes. So this, okay, few words on this. So G-2 is really a measurement of the muon anomalous or the magnetic moment of the muon. So the muon has what was originally called an anomalous magnetic moment, but you can measure it in quantum electrodynamics. You can calculate it to many places of decimals. Even in the standard model, you can calculate it to many places of decimals. It's a very sensitive measurement. It can be done very sensitively. The point is that the numbers which we are getting seem to have some discrepancy with the experimental numbers. So I'm not sure what will be revealed tomorrow, but I mean, over the years, this has been an up and down task. I mean, often, we have seen both things. I mean, the discrepancy of G-2, it's become quite big now. But it's a difficult thing because at the energy of the muon, calculations where the strong interaction is involved, which does happen at higher orders in perturbation theory, become very difficult to do. So there's some fitting and this and that to be done for that. It's a technical thing, but the calculations become more and more difficult. What has happened is that over the years, I have seen that sometimes the experimental, there have been discrepancies. Then either the experiment has been redone and the number has changed and become closer to the theory, or somebody has pointed out a flaw in the theoretical calculation because these are very long and complicated calculations. Most of it is done by the computer. So somebody found a bug in the computer program, corrected that, and again it became closer. So I would be very glad if it were really confirmed that there is some real discrepancy between the theory and experiment in that, but I'll keep an open mind on this. If it is found, then of course there must be some other kind of force, other kind of interaction, some new kind of particle, which is the exchange particle of that. I would love to see that. but I'll wait for more confirmation before I sort of put
Okay.
my money on it.
Yeah, let's end with the last question. It's a pretty basic one. Kunj Bachani is asking, you had mentioned earlier that electrons repel each other. So no two things really touch each other. How then do we feel things with the sense of touch?
Well, you don't really touch. It's the electrons interacting, and then you have nerves in your hand, and the nerves feel impulses. It creates chemical changes in your nerves, and that's what you feel as a touch. You don't really touch.
Yeah, I think
so. If you go down to a very small length scale, you don't really touch.
Yeah, I think that's all the questions I think we have time for. Actually, there are a large number, but I had to select some of them. So let's close for the day, and let's thank Sreerup for a wonderful talk.